All right, next section is 3.7, the chain rule. This is an extremely important rule that is used throughout many areas that involve calculus. The chain rule is an extremely important rule of differentiation. It can also be a little tricky for some people to get a hang of immediately. This is definitely a section you want to practice and work lots of problems on. So before we even talk about what the chain rule is, we're first going to take a look at these table of functions, and they are a composition of function. If you remember, a composition is when you put one function inside of another function. In other words, you take one function and you use it as the input into the other function. So here, what we want to do on this table is just write down by identification what the inside function is and what the outside function is. This will be extremely useful for helping us compute the chain rule, because the chain rule requires us to look at an expression and in real time be able to say, okay, this is the inside, that's the outside, then we can differentiate it in this manner. So here, inside function would be x squared, outside would be sine of x. Inside function, x squared plus 1, outside function, square root of x. Inside function, x over x plus 1, outside function, tangent of x. Inside function, 3x squared minus 2x, outside function, x to the fourth. Lastly, inside function would be x squared, outside function would be e to the x. Okay, now the chain rule here says the following. If you want to take the derivative of a composition, so if you have an inside-outside type of function, and you want to take the derivative of that full thing, then you have to differentiate the outside function while leaving the inside of the function alone. Then multiply by the derivative of the inside function. Okay. So to see this in action, let's go ahead and we'll come up here and we will do example 1 up here. Okay, there's plenty of room up here. We'll just go ahead and do that. So let's take a look at this function sine of x squared. So let's go ahead and just say sine of x squared. What we could do here is really quickly is, what if we do the following? Let's say u equal x squared. Then the sine of x squared is just the same thing as the sine of u. So now what we could do here is take the derivative. So let's say this is y. Let's just say y equals, okay? So let's just say we want to take the derivative of y now. Well, we could do it with respect to x, which is ultimately our goal, but we could do this intermediate step here. So let's just go ahead and look at this as y equals the sine of u. So now, dy du is equal to, well, derivative of sine is cosine. That's it. But here's something else. We also know that u is actually dependent upon x. So what about the derivative du dx? Du dx is 2x. Now here's the interesting thing. The chain rule, although the chain rule is written down here using this function notation, I didn't write this in function notation. I didn't say f of x equals sine of x squared. I just said y. And I said, I didn't write u of x. I could have, but I just chose to keep it as u. So there is another way to write the chain rule. Another way to write the chain rule is the following. So if, let's say, y is a function of u, and u is a function of x, then the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. This is also the chain rule. And it looks a little bit different than it does down here, but that's kind of what this is. This first term is just dy du, and this second term here is du dx, because in this case u was the inside. So this way to think of the chain rule is just multiplying two derivatives is extremely useful, and not enough people think of it this way, and it's very important for them to do so. So in this method here, we can kind of just see what we need to do here. So in this case, if we use this for sine, then dy dx is equal to cosine of u times du dx, which is 2x. But here's the thing. This might look a little strange to you because there's a u and an x, and it just might seem a little odd. Well, here's the thing. This u is sort of artificial. We just introduced it to make our derivatives easier. We really ultimately don't need u, because if we look at the original function that we were differentiating, there is no u present. So we should probably get rid of the u's, which we can do because we know that u is equal to x squared. So we can just take this a step further and replace cosine of u with cosine of x squared times 2x. And that's our derivative. Okay. So I don't want to go through this entire explanation for each of these, but that is definitely worthwhile to see doing it this way. So the other way to do it is if we're just going straight to the answer, ddx of sine of x squared, I just see that sine is the outside, so what's the derivative of sine? Cosine. I'm going to leave the inside alone, so I'll just copy paste, and now I have to differentiate this, which is 2x. This method here is generally what we do 95 or more % of the time, but it is very useful in some circumstances to think of the chain rule as a product of rates of change. So that's why it's worth it to show you. So we will continue doing it this way. So let's go ahead and erase this stuff that we don't need really quickly. And we'll go ahead and just bring that up. So there's the one derivative. Next derivative, we're going to take the derivative ddx of the square root of x squared plus 1. But remember, this is the same thing as just x squared plus 1 to the 1/2. So if we differentiate it written like that, this is, well, just put blinders onto this for a second. Pretend for a second that this entire thing is just x to the 1/2. What would you do? You'd bring the 1/2 down and subtract 1 from the exponent. That's your power rule. So right there, what I have written currently, just this, is the derivative of the outside. Then we're going to leave the inside alone by bringing it over unchanged. And then we will multiply by the derivative of the inside, which is 2x. There you go. Moving on to tangent. So the derivative of tangent of x over x plus 1 is, this might get a little big because in the inside we have a quotient. So the derivative of tangent, we've learned recently, is secant squared. And then we want to leave the inside alone. And then we're going to multiply by the derivative of the inside, which is a quotient rule. So derivative of the top is 1 times the bottom left alone minus the top left alone times the derivative of the bottom all over the bottom squared. There we are. Okay, down here, d dx of 3x squared minus 2x, quantity raised to the fourth. Again, this is the inside. The outside is just the raising to the fourth function. So we should just put blinders onto the inside and differentiate it as if it were x to the fourth. So this would be 4 inside to the third. So this would be 3x squared minus 2x times the derivative of the inside, which is 6x minus 2. Lastly, the derivative d dx of e to the x squared. The outside is e to the x, so the derivative just stays e to the x, but our inside is x squared times 2x. All right.